Hello everyone, this is Dr. Hopkins. We're starting a new topic today, moving away from acid-base and going on to the concept of solubility. So first thing we're going to do is kind of review things we already know, a little bit of definitions and so forth. So a solution is a homogeneous mixture of what we call the solvent, so that's the major component, what's mostly in the solution, and a solute or solutes, multiple of them can be, which are the minor components. Now what we know already from first semester is that we can measure the amount of a solute in a solution by its concentration. And we have our units that we were very familiar with. Molarity, we used it in the lab, used it in class, which is basically moles of solute divided by the volume of solution, so it's moles per liter. Now there are some other units that you might see or you might encounter. One is molality, and that's moles of solute over kilograms of solvent. And then parts per million, and actually parts per million is just a subset of a mass by mass concentration unit, but parts per million is one you'd often see. Sometimes you'll see parts per billion as well. So parts per million is milligrams of solute divided by kilograms of solution. That should say solution, not solute. So milligrams to kilograms is 10 to the 6th, so it's 1/1,000,000th of the total mass. So molality is something that's actually pretty similar to molarity for dilute aqueous solutions. Part per million or part per billion, so ppm or ppb, is something it's a concentration that's often used in regulatory environments such as the Environmental Protection Agency. So we're talking about concentration of a contaminant in a water supply. It's oftentimes published in terms of ppm or ppb. So let's look at converting between these concentrations. We know how to do molarity, so the molarity to molality. So molarities are kind of standard. We're going to go back and forth between. To molarity to molality conversions, you have to use density, okay? So just using density, because we're just going from liters to kilograms in terms of our overall liters to kilograms. We're not going to do any example problems of that. Most of the time you won't see molality. But molarity to part per million conversions, we might as well do a little bit with this, and vice versa, going from part per million to molarity. So you need to use both the density and the molar mass. So let's take an example where we have the Safe Drinking Water Act by EPA establishes the amount of copper in water that you drink, so out of the water fountains and so forth, should not exceed 1.3 part per million. Let's determine what that concentration is in molarity. And the second part of this, I'm going to go ahead and do them both, is what would the part per million of copper be if the concentration of copper nitrate is 0.001 or 1 times 10 to the minus 3 molar. So here we have our problem set up where we have 1.3 part per million. I haven't put copper there, so that's 1.3 milligrams, it should be an M, of copper 2 plus over 1 kilogram of solvent, despite what I had on the previous slide. So what we need to do is we need to convert that into, in the end, moles per liter. So our solvent is water, and so the density is 1.0 grams per milliliter, or more importantly, kilograms per liter. So if we multiply by the density, we would get rid of our kilograms, and now we have it in milligrams per liter. Okay, and then I'm going to go ahead and convert it to grams, so it's 1,000. There's 1,000 milligrams in grams, so we're dividing out the milligrams. So now we would be in grams per liter, and the way we convert, and I'm going to go ahead, I don't have enough room on the other side, from grams to moles is we use the molar mass. So we look it up at 63.55 grams per mole. So that's the of copper 2 plus. And so then if we multiply all of that out, we end up with 2.0 times 10 to the minus 5 molar. So that's our concentration, or in this case, it's moles per liter. Everything else has canceled, so we're at moles per liter. Okay, that would be our concentration. So you can see 1.3 part per million is not a very high concentration. It's at most, 20 micromolar, if we will. Okay. So now let's take our 1 times 10 to the minus 3 molar copper nitrate, and let's figure out what's the part per million of copper 2 plus. Now remember, we can't find a bottle of just copper 2 plus on the shelf. It's a salt. It's always going to have an anion. So we're always going to have something like nitrate or chloride or something associated with our copper. So let's say we made or we found in the lab a 0.001 molar copper solution. Let's figure out the part per million. The first thing we need to know is that this is 1-to-1 copper 2 plus to copper nitrate. And that's in moles. So the mole ratio, so for every 1 mole of copper nitrate, we get 1 mole of copper 2 plus. So that means the concentration of copper 2 plus that we generate would be 1.0 times 10 to the minus 3 moles of copper 2 plus divided by liters. So that's our molarity. And then we're going to use our density. So this is density of water, which is our solvent. And then, so we get rid of our liters, and we put it to kilograms. And now we need to convert this to grams. So get rid of moles. So it's 63.55 grams per mole. That's our molar mass, right? So now we're in grams, and now what we just need to do is multiply by 1,000 to get in milligrams per kilogram. And if we do that, we end up with 63.5 part per million. Okay, so it's a little higher than the standard 1.3 above. So we have 63.5. Now, if I ask the same question about part per million of nitrate, that's a little trickier because they are your 2-to-1 nitrate to copper nitrate because of this. And so that means we would end up with a concentration of 2 times 10 to the minus 3 moles of NO3 minus divided by liters. And then we would go through this process, 1 liter per kilogram. The molar mass is 62 grams per mole times 1,000. And we would end up with 124 part per million. Okay, because part per million is a mass-based. So even though it's the same component, we get almost twice, the part per million of nitrate that we do of copper, mostly because the molar mass is similar in this case. So that's how you convert back and forth between molarity, which is our units that we typically use in the lab, to part per million, which is a unit you might see in a regulatory environment. Now let's briefly go through kind of what makes something soluble. So solubility, and we're going to consider, because actually what makes something soluble is actually dependent on what our solute is and what our solvent is, very detailed in terms of the structure and so forth. But let's think about this in terms of thermodynamics. So we know that enthalpy, it's when we were talking about particular molecules, the enthalpy was related to the bond strength, so the strengths of the various bonds of your molecule itself. Now, if we're talking about enthalpy between substances, it's related to the intermolecular forces, so not the bonds, but the intermolecular forces, so not the covalent bonds, but the intermolecular forces. And so we would have to think about this from a standpoint. So if we have a solid, it has intermolecular forces, so we could list them: hydrogen bonding and polarity and all the things that you learned last semester. And then we have the solvent independently, right? So those have intermolecular forces, and they clearly, as a solid and a liquid, they like each other. They're not gases, so there's intermolecular forces there. Versus what would happen if we put the solute in the solvent. So are there favorable intermolecular forces? So in other words, is there hydrogen bonding between the solvent and the solute that would make it favorable to go from a solid to a solution or from a solvent to a solution? So you'd have to weigh all the intermolecular forces. So for example, if we had sodium chloride, clearly we know that sodium chloride in solid has this ionic bonding between the sodium plus and the chloride ion. And the only way you're going to get sodium chloride to dissolve in water is if these polar interactions shown in the second part, so the partial negative of the oxygen of the water interacting with the sodium and lots of waters around that sodium, that net enthalpy has to be favorable for solution formation in order to break apart these ionic bonds. So that's the enthalpy part of it. Now there is, in thermodynamics, another part, there's entropy, and that's related to the difference in disorder. It's a little trickier to discuss entropy, or at least to have a simple picture of entropy. If we have an undissolved solid, the structure of the solids are typically very ordered, right? So they're very, they're not high entropy, they're very low entropy, okay? And then what's the entropy of the solvent without the solute? And that is tricky to decide whether it, what its overall entropy is. It could be very ordered, it could be somewhat disordered. And so versus the disorder introduced when we put the solute in the solvent. So typically the solids are very ordered. We put them in a solvent and now they're going to disorder, they're going to spread out. So that's an increase in entropy. So that is something that is favorable to solubility for just about all solids. The trick is whether the solute orders the solvent or makes it more disordered. Okay, so it's a little bit trickier. But in the case of sodium chloride in water, for example, I talked about this briefly, the dissociating sodium chloride into sodium and chloride ion is increasing. We're going from 1 to 2. So we're increasing the disorder overall. And we're going from 1 to 2, and those two are surrounded by waters, like we represented in the enthalpy part. Okay, so that's also increasing the disorder. So in general, solubility is an entropically favored process. Not always, but in general. So in the end, if we want to know whether we get solubility, we have to use delta G, or our free energy, and delta G is delta H, so it's the enthalpy part, minus T delta S, which is the entropy part. And if both of those line up, or one of them lines up and it's bigger than the other one, and it's less than 0, you get something that's soluble. Okay, and so that's all dependent on structure. The devil is in the details in this case. But when we have a delta G, we can also get a K, which means eventually we're going to get to an equilibrium of solubility. So basically, these are the kind of takeaways from the lab, or from this video. So the concentration we've dealt with. We have a couple new units of concentration other than just molarity, and that we know that the solubility, predicting the solubility would depend on the two components or the multiple components involved, the intermolecular forces, and the entropy involved, right? So there's the thermodynamics of that process. But once we get that thermodynamics, or vice versa, if we have an equilibrium constant, we can determine the thermodynamics of that process. So we're going to use equilibrium in the next time.